Feedback. I think that should be fine. So how it's going to work out. Oh, I'll turn off the speaker. Oh, the projector. So there's no microphone. Turn off the sound. What's happening with the microphone? Okay, I think we can start. Do you know what it's downloading? It's downloading PowerPoint. Downloading. I thought it's already downloaded. then go to the, keep it open, keep it open. Go to Google Chrome. Go to the other one. Okay, I think start this one.
Okay. Good evening, everyone. So some of you might have already listened to this talk. I presented it as a part of my qualifying exam a couple of weeks back. So most of it's going to be same, but I've added a couple of new slides. Uh, so today I'll be talking about oceanic variability on US climate and its extreme in a regional climate model. So what are the key questions? Why do we need to do this? So essentially we are trying to study, so does the variability in the surface and or lateral boundaries of a domain lead to increased likelihood of extremes within the domain? So let's look at some of the examples first, how remote variability would affect the climate and as well as extremes over the United States. So here is an example of a 1993 Midwest flood case which happened in uh, start in the first week of July of 1993. It was a pretty intense flooding event over Midwestern United States, and in the literature, so there are these three reasons. If you look in the literature and study this, you will find there were like three main reasons identified. One of them was there was a greater cyclone activity over Pacific region, which moved inland. There was also increased moisture transport from the Gulf of Mexico, as well as the North American jet itself shifted southward. Uh, so, what for the talk, what we are trying to study here is how the cyclone activity over Pacific, over the Pacific would affect. And recently in 2013, Christina Patricola, uh, she did a study with the regional climate model, wherein from the lateral boundaries over the Western Pacific, they removed all the synoptic eddies. Any frequency less than 10 days were removed, and compared to a control case. And what she found, she essentially found the results to be counterintuitive in a way that even when the cyclonic activity, the synoptic eddy activity from the Western Pacific were removed, the precipitation anomalies over United States for that particular period is still positive. And the main reason for it is essentially because removing the eddies from the western boundary affected the mean circulation itself. And so what essentially we need to keep in mind here is that just filtering out the synoptic eddies may not be the response may not be as simple as it looks like. It would interact with the mean circulation. So what about the temperature extremes of like hot spells and cold spells? So let me look at one. Let me give a brief introduction about one such extreme event called heat wave. So how do you define a heat wave first? So heat wave is a prolonged period of excessively hot weather, which may be accompanied by high humidity. So on the figure bottom, you have an example of such an event which happened in mid-March 2012. So what you see here is the surface temperature anomaly, and you can see that it's a pretty strong response. It's a pretty intense extreme event, which is engulfing quite a lot region of United States.
Hold on, just can you hear Tarun?
Sorry?
Can you hear Tarun?
Yeah.
Okay. You're doing something complicated, but if you can hear, that's fine.
Yeah.
What's the value of that vector approximately?
So
That like 1 degree, 2 degrees, or 5 degrees?
it's
The ballpark.
I think it's of the order of 4 to 5 degrees. Okay, so why heat waves? So here is an example. Here is an example of heat wave effect, like how these heat wave effects can affect the mortality. And here is an example from Borden et al. Study in 2008. And so what you see in a pie chart is the natural hazard deaths by event type over United States from 1960 to 2005. And you see close to 20% is what is accounted by heat and drought. So it's a significant uh, and another effect of heat waves, another important effect of heat waves is you can see in this particular figure, which is from the figure at all 2006. What you see here is a bar graph of summertime burn area over Portugal, and this one big bar which stands out for the 2003 European heat wave. So these events are very uh, have a great social and economic impact as well as on the on the on the on the on the mortality rate, and they're very important to study. So this is about why you need to study that. But when you're doing a analysis of a data, you need to identify such events.
So Tarun, I don't think we are seeing this. Can you go back to this PowerPoint window without the slide? Do it there.
Okay, I think I should do this. It's moving there.
Yeah, they're not seeing this. There must be a way to fix that.
We should be able to. Okay, so how do we identify heat wave in the data? So the definition which I have used is as follows. A period, so first thing is we're using a daily temperature data, and in daily mean temperature at 2 meters, a period is considered a heat wave if the temperature is above 97.5 percentile threshold for at least 3 days. The average temperature during the whole period should exceed again 97.5 percentile threshold, and the temperature for all the days in the period should be above the 81 percentile threshold. So you can see that I'm using two thresholds. So the definition is a two threshold definition, and the thresholds are, these are not absolute thresholds. They are the percentile value. So they will change from place to place, and essentially you don't want to have a geographical bias. So use a relative threshold, and two thresholds are used in order to account so that you don't have any false break in a heat wave. What I mean by that is, so let's consider a one extended period in which if you have just one threshold, what would happen is, so because of the natural variability of temperature, if the temperature goes down the first threshold, what would happen is it would split the heat wave, which we don't know. Essentially, it would create a bias. So we use two thresholds, 97.5% thresholds and 81% thresholds, in order to prevent that situation. Now, and at the bottom figure, you have an example of how in a daily temperature, data, how the heat waves would look like in this case. So the blue is the daily temperature data, and the shaded region is the identified heat waves. So you can see for 1993, it goes from May to September, 1984, May to September again. And another thing to note here is, so the heat waves, according to this definition, according to the way you calculate the percentile, you see a lot of heat wave activity in particular year. So you can see that these are what I'm considering here is the much more milder extremes, or milder heat wave events rather than one which happens 1 in 2 or 3 or 4 or 5 years.
So Tarun, I think we can fix the go back to Google Hangouts. You share the whole screen. I think that is it. So go to the top, the left side. left side, go to the green thing, click on the next one, the green, yeah, click on that, click on it again. There's full screen. That's good, yeah. Now you can go to full screen part. See if that works. Yeah.
Fantastic.
Yeah, fantastic. So it's working.
Okay.
Yeah, it's coming through.
So this was the we learned the synoptic atmospheric variability example of that. Then I moved on to explain what kind of a heat particles I will be talking about. Now let's talk a little bit about the other part of the talk in which I'm looking at how the surface boundary conditions, essentially the sea surface temperature on intra-annual variability of sea surface temperature would affect the climate and its extremes in the domain. So what do we know? A little bit about what do we know already about. So ENSO, El Nino Southern Oscillation, is one such largest known source of intra-annual variability. Some teleconnections of El Nino Southern Oscillations on the United States. So northwest and southwest United States have a contrasting response in precipitation to the El Nino Southern Oscillation. There is a positive correlation with Texas and central US rainfall, though this is a bit shaky. And in certain studies, they have also found that the future changes in the teleconnections linked to the change in the mid-latitude base circulation would affect the extreme events. So it's not just it's a complex situation. And also, winter storms and the precipitation variability is significantly impacted by ENSO. Okay, so essentially, just to wind up this part, so essentially I'll be looking at the effect of synoptic variability as well as effect of intra-annual variability of sea surface temperature over on rainfall, temperature, and extremes over the United States. Why do we need to study this? Essentially, the one-line answer for that is we want to increase the predictability of extremes over United States, and we are looking at the remote sources of variability, remote sources of predictability of the teleconnections. So before going to the modeling study, let me talk a little bit about some observational analysis which I have done. So the question here is, what is the response of variability to the change in mean from a regional perspective? So what I have done here is taken temperature and precipitation data from North American regional reanalysis over contiguous United States, and subdivided the domain into 6 by 6 degree box. And what you see here is for a particular month of June rainfall. What you see here is a scatter plot between a mean rainfall for the June as well as the monthly variance of a rainfall during that month. So what each dot here would represent is one particular box over the United States for one particular June, and what was the mean for that? And it's an anomaly. Remember that. That's why there are negative values. So each box is for one particular June. It could be June 79, June 80, June 2000. And what you see here is you see a very clear relationship between a variance and a mean. So the mean, as the mean increases, the variance increases in a rainfall, in a summertime rainfall. And not just that, you see also, it's also the envelope itself becomes larger. So the variability also increases with mean. But what about the temperature? If you do the similar scatter analysis for the temperature data for the same month, what we see here is we don't see much any relation. It could be that what essentially it says here is the mean temperature, either if it decreases, tell anything about the variance. It will depend on case to case. Okay, so let's look at, instead of looking at a summer, instead of looking at a June, let's look at a January. How would that look? If we do a similar analysis, we do see a opposite relation as what you see, the contrasting relation with the rainfall. So essentially to summarize this, there is no relation in June in the air temperature, but there is a inverse relation between mean temperature and variability of the temperature. So why would this be? So in case of a rainfall, this is the result directly from a mathematical implication. As you know that the rainfall, the distribution is highly skewed positive distribution. Usually people represent it in some form of exponential. Gamma distribution is what is used very often. And what you see, and I'm going to show you an example of the gamma distribution here. So what you see here is this is the rainfall rate and this is the PDF. So these are three different values. As you can see, as the variability increases, so the black line has the biggest variability, and the orange has the smallest variability, or the spread, or in other words, you can also talk in terms of a scale of a distribution. How wide is the distribution? So as you can imagine, the variability and rainfall, mean rainfall, has a positive relation. Greater variability means greater mean, or vice versa. But in the case of a temperature, it's the mean surface air temperature is not related to variability during summer, but is inversely proportional during winter months. So there's a physical cause for this. Would be in essentially in the winter time, the variability is essentially because of all the colder events. The colder events determine the variability during the winter season. That's why you see the figures which I have shown before. Well, I missed a point here. So why we need to study this variability and mean? Let me just stand that first before going to the next part. So essentially, like a lot of times, the discussion comes in a global warming scenario when people talk about, okay, if the mean changes, if the mean temperature changes, what would happen to the variability? Okay, essentially, when the mean changes, what would happen to a variability? So essentially, so that was that's mostly in a global scenario, but in a regional perspective, it would look something like this, as you've seen here. So now let's move on to the modeling results. So first, what are the model details? So the domain is shown in the figure here. So it's a box model 3.3. It has 27 kilometer horizontal resolution, 28 levels in the vertical. The physical parameterizations are as follows. And also all this model runs were done by Christina, and you can refer to the paper if you want more details about the simulation. Okay. So how do we study the study methodology? So in order to study the remote influence of intra-annual variability of SST, what we have done is it's summarized in this table here. So there are two runs, walk observe SST and walk climatological SST. So essentially, because we are studying intra-annual variability of SST, so the SSTs are modified. In walk observed SST, we have a observation of SST from 1981 to 2000 monthly. These are monthly sea surface temperatures from a Hadley Center SST data, and in the WAF climatological run, instead of using year to year, the SST we changes from year to year, we have just used a climatological SST. So essentially, in this, what you are doing here is you are filtering out any intra-annual variation in sea surface temperature in the boundary condition, sea surface temperature boundary condition, and natural boundary conditions are observed in WAF of SST, and anything greater than 28 days is filtered out, but the season cycle is added. This is done just to make it consistent with the lower boundary condition. The second sets of experiments are summarized in the next table. So in this, we will be studying how the Pacific synoptic variability influences the climate over the United States. So in this case, again, two boundary conditions, SSTs and lateral boundary conditions. So in WAF observed SST case, both of these are observed, but in WAF low 10-day case, the SSTs are observed, same as what in the previous, but anything greater than 10 days are filtered from the western boundary. So the western boundary is right over here. So this is the western boundary. Okay, so what are the results? So let's look at first the remote variability of intra-annual variability of SST, and how does it affect the heat waves over the United States. Okay, here's the figure. So essentially, what I'll be showing you, so the responses would be all it would be in a term of a difference figure between the two runs. So in this case, what you see on the left here is the change in heat wave days per year, and it's the difference between WAF observed SST and WAF climatological SST. So what you see here is, so in an observed, so the brown color or the red color here means that the observed SST case, in which the run in which there was a greater interannual variability in the sea surface temperature, had greater number of heat wave days, the mean value, these are the mean values, had a greater number of heat wave days. As you can see, the most of the domain you see a brownish color. And just to give you an example, just to give you a value, so how much, whether this is a significant change or not, we can, so this the maximum change is close to 6 heat wave days. And if you, and this is on the left side, what you see is the heat wave days in the observed SST. If you can compare both of them, you can see that there's close to 25 to 30% change, which is a significant change. So let's look at this particular box, and let's look at the time series, how the internal variability changes. So let's focus on the solid lines. The pink one is for the WAF observed SST case, the blue one is for WAF climatological SST case. And the first observation here you can see here is, so the WAF observed SST case has greater internal variability. You see greater fluctuation with the years. As well, on the other hand, the climatological SST, the internal variability is decreased. So and as well as if you see the mean difference, if you do the mean of this time series for both, there is close to 3.5 heat wave days over this, as you can see even in the previous average figure. And so why would this be the case? So let's look at heat waves relation with the mean temperature as well as the lag-free autocorrelation. So essentially, to think of it as, you can think of it like a particular year would have a greater number of heat wave days if that particular year had a greater mean temperature with respect to other years. So that would be one very simple link. The other link would be if in any particular year, if you would think there is a short-term persistence in a temperature, day after day, short-term persistence in a temperature, you would again think it should increase the chances of heat wave happening in that particular year. So what you see in this figure is the blue line is same as what you seen in the previous figure, the heat wave days. The pink line is the mean temperature for that particular box, and what you see in the yellow line is the lag-free autocorrelation, which is essentially a degree of short-term persistence. And in the boxes, you have is the correlation value between the two time series, between heat wave days and the mean temperature. It's close to 0.843, which is substantial correlation, and between heat wave days and the short-term persistence, it's 0.589. So this was for the WAF observed SST case, but what about what changed in WAF climatological case? So as you can see, this is a similar figure, but for a WAF climatological SST. So again, the blue line is the heat wave days, the internal time series of heat wave days. The pink is the mean temperature, and the yellow is the autocorrelation. So you can see that the correlation with the mean temperature is still pretty much high, but the correlation with the short-term persistence has decreased. And if you do a significant study, you would expect at a 95% confidence level, you would expect the minimum correlation to be 0.440. This is if you consider this all the 20 values to be independent of each other, not correlated with each other. So okay, let's move. So before going further, let me add on a few more things. So as you can see in the pink figure here, the 1982 and 83, you see a very big peak in heat wave days, which happens to be a El Nino year. Whereas on the other hand, 97, 98 is also a very well-known El Nino year, but you don't see much effect on the heat wave days. So this is an interesting problem, and we'd like to study why is so the case. So done just a preliminary analysis here. So this is just to reiterate, this is just a oceanic linear index uh, for 1982, 83 versus 97, 98 case, and the 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 warmer colors means El Nino, the blue color means uh, the La Nina, and these are for the months, different months. So as you can see, in 82, 83, so 82 we have a big El Nino event, as well as in 97 also you can see these two patterns very similar pattern. But then why would that be the case? Is what we are interested in. Okay. So what I've done here is I've picked out these particular years, 82, 83, and 97, 98, and these are the heat wave days. As you can see, there is a substantial difference. So 82, 83 you see over the central United States, over in 83 you see over the central United States there was a big heat wave event. The heat wave days were greater than others, and as well as in 83 case you see also a very big heat wave event, but the extent was more towards the eastern parts of Midwest and eastern part of the United States. But on the other hand, 97, 98, it looks like, which is another El Nino year, it seems the response is very different between the two.
What's going on in Michigan? Why is there everywhere else?
You mean right here?
Yeah. What's that?
There's a big lake there, that's right.
Yeah, I know. Okay.
On both sides.
Up here in Minnesota, so yeah.
That's an interesting.
Well, I can guess whether in 20 years does Michigan ever have heat wave.
I can do that.
That's it.
Okay.
So,
I need to get back to doing that. And I don't know, it's a very big difference. So one is on top of the right, it's around 60 and this is around 50. Yeah.
But none of
Let me get back to you on that. Let me double check this.
just wanted to make sure it wasn't that way.
Let me double check this. Okay, but you see a lot of difference from year to year, though both of them happen to be a similar internal variability uh, years, but still you see a very contrasting difference between the two. So I've done this. So I've done another plot wherein we look at the soil moisture on the ground. Is it anywhere related to the heat wave days? So what you see here is, again, these two are the top figures what I showed in the previous plot, but on the bottom I show you, I plotted a soil moisture for particular year, and the, 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 the warmer color here means less soil moisture, whereas the blue means there's a greater soil moisture. So as you can see that, like over in 1982 there was a so there, in 1982 there was a lower, since it's a warmer color, so there was a lower moisture, whereas in 1983 again it was a lower moisture, but so just in case, remember that this is not a different plot, so it might confuse you, but this is okay. But what about the 97, 91, and 98?
how do you infer cause and effect? Cost.
So I'm still not saying that this is the cause. I'm just trying to find if there is any relation between soil moisture, or if there is, if the heat wave signal you can inform even from the soil moisture from now. Mention that. But for 97, 98 case, again you see a very similar pattern in soil moisture. Like it's always drier over central United States. It's always drier over California, Southern California, Arizona region. So okay, let's instead of instead of looking at a spatial plot, let's look at so if I pick the one particular grid point over somewhere over this region and plotted a time series. So on top, what you see here is again what you have seen before. This plot you're familiar with. It's the daily temperature data, and these are the shaded regions are identified heat waves. So 1982, 83, 97, 98 on the top panel, and on the bottom panel you see the time series for a soil moisture. And again, the heat wave regions identified is again marked in the shaded region. So as you can see, one okay, there are quite a few observations I want to make here. One is why, let's consider a case of 1983, why there were so many heat waves identified, whereas in 1997 there were not many heat waves. So one straightforward factor here could be that the mean temperature for 1983 is much higher. If you see, the time series is much more higher in this region. If you compare it with the 1997, it seems to be much lower. So again, so the mean temperature is responsible for that, as well as so I think it's not just the mean temperature, but it also depends on it depends on other variabilities also. Short-term persistence as well as you see there's this uh, close to 20 days, 25 days cycle. And if you look at the soil moisture figure, what you see here is in 1983 there was a big dip in the soil moisture, but in 1997 case it didn't. 1997 and 98 it doesn't look like, though it kind of dips towards the end of the season, but there were no there were essentially no heat waves are identified. So there is some relation with the soil moisture. Means you do see a response in soil moisture in case of 1983, whereas not in case of 1997 and 98. So essentially, I want to tell here is So I want to remind here is 1983 and 1982, 1983 case was also a very intense drought period over the region. So it could be that the the heat wave days. So these are so you have to remember that heat waves. What I'm considering, they are much more milder, and they are not very long-term extremes. They are short-term extremes. So in 1980 to 1983 case, it was a drought period. So you can see that it kind of dipped, and the temperature shooted up. So there was a bigger, instead of a short term, there was also a bigger lower frequencies which might be responsible for it.
But isn't the heat wave worse when it's more humid? Because
Okay, so that
the effect of heat wave, isn't it worse when it's more humid?
right. So
Because your body can't cool by sweating.
exactly. But I think in this case, if that's the case. That's the case. So it depends on how you define a heat wave.
I think if you have the
If I have a indices which takes
heat
into account
index,
of humidity, I would see. I might as well see.
Difference also in heat wave.
no, but in real life, I think
Yeah,
it
it
does
doesn't make a difference. Why?
Yeah.
Real life.
Yeah, 50 something like
heat index. Like in the statistics, gets complicated.
And moreover, again, I think it would depend on if people want to study the mortality and how it affects the health. They would like to look at the heat index. But if people are more interested in the meteorological causes and conditions, then humidity may not be a
Yeah, but I think if you just look at 4 cases, you can't really draw any robust conclusion.
no, not robust conclusion. So this is just a very preliminary analysis. I want to just look at how this. So essentially, the reason behind it was like essentially the other day we talked with Dr. Peng. He said, okay, why a short-term persistence? What is responsible for a short-term persistence? But so in the discussion it came out, it could be the soil moisture, which is uh, the soil moisture content is what is controlling the heat wave days. So I wanted to just look at the heat, how the soil moisture time series looks like and how the station works.
But you can ask questions, are the heat waves more common during drought years?
So according to this definition, it would be.
Which definition?
According to the, if you base your definition just on the temperature data, it would be because
Drought years are warmer.
drought years are warmer. Okay. So
The worst Dallas heat wave was maybe a couple of years, 2011, right? The 100+ degrees. 100 days, over 100 days is 100+.
So yeah, it has some control from a longer term variability also, how the droughts and heat waves. Okay, I'm going to skip this.
Maybe wrap up fairly soon. We started late.
Okay, so the next part I want to just give you an example of how the lateral boundary, the synoptic eddies coming from the western boundary, would affect the mean rainfall and the temperature. So here is a mean response for a rainfall and a temperature. On the left you have a rainfall, mean rainfall, and on the right you have a daily air temperature. So these are a little bit changed because of the PPT, but it is low 10-day minus observed SST case. So as you can see for a June-July, there is a mean circulation change in both rainfall as well as temperature. You see, so low 10. So just to remind you, so low 10-day cases when we have filtered out the synoptic eddies from the western boundary and observed SST is the control case. So as you can see, there is still a positive anomaly over central United States. Over the central United States, even when you filtered out the synoptic eddies coming from the western boundary. So this is something which has been already studied by Christina Patricola, and I've explained that it was in this case probably the mean circulation change in such a way that the moisture from the Gulf was carried over in the low 10-day case, even when there was a less synoptic eddies from the west. But more interesting here is the case for daily air temperature, wherein you see it's almost all red. So what it says is that if you don't have a synoptic eddies coming from the west, it almost uniformly warms up the United States, and with the two peaks located, one over the western southwest United States and one over the Midwest. And what about the variability? So variability, as you would expect in the temperature case on the lower right side corner, it's all blue. It all says the variability has gone down uniformly over, not uniformly, but almost over the United States, which is as expected because you are taking out the synoptic eddies coming from the western boundary, but the response and the variability of rainfall is still complex. So, what about the time series? So, if you consider a box over a California, and if you plot a time series for both observed SST and low 10-day case, so these runs were 5 ensemble members. So the black line here is the mean of ensemble, and the different greens are different ensemble runs. So as you can see, one clear observation from this figure is so filtering out the synoptic eddies from western boundary, it looks like it's nothing. It's acting as a filter. It's smoothing the time series, temperature time series, and if you look at another box over the Midwest, though it's not as clear as in the case of the western boundary, but still you see that the peaks are a little more smooth. The peaks and ridges are almost a little bit smooth. So it acts like a low pass filter. It's smoothing the temperature time series, as well as if you look at in the low 10-day case, there is a greater spread among the ensemble members. So it's affecting in such a way that each ensemble member is less constrained. Why is it so? We're still thinking of the reasons for that. Okay, now let's look at what the upper air circulation looks like for the same period. So as you can see, there is a great similarity. What you see here is it's a 500 millibar geopotential height difference between the two runs on the right, and on the left is the same figure what I've showed, the temperature response. So as you can see, similar responses in surface temperature and 500 millibar heights. It indicates that synoptic eddies impact surface temperature due to changing the mean upper air circulation. And so this is just a summary, and I would like to wind up. If you have any questions.
Why don't you go over the summary?
Okay. So we found a contrastic variability mean relationship between rainfall and winter time temperature. So variability in surface, and so the one conclusion, main conclusion from here is, so variability in surface and natural boundary conditions can have a nonlinear impact on mean state. This part, the third point, haven't shown the results to you, but essentially what we found is that change in mean rainfall state dominated over a direct impact of a variability. Essentially, what we see in this case is when the sea surface temperature variability was reduced, the rainfall variability in the United States was still, it was greater than in the case when there was a greater boundary variability. So it kind of tells us that there is a counterintuitive behavior possible, that is, increased boundary condition variability can lead to reduced rainfall extremes due to a decreased mean rainfall, and the link for this is in the first is the mean and variability are positively correlated, and the changes in mean temperature are less important in affecting extremes. Year-to-year heat wave activity is sensitive to remote SST variability. Increased persistence in observed SST runs is sensitive to more prolonged heat waves, and removal of synoptic eddies from the Pacific in mean circulation over the United States. That will be it. Any questions?
You want to click the full screen? Let's go to Hangout. Okay. Any questions from the remote listeners? They're all muted. Chris?
Yeah, actually, can you guys hear me?
Yeah, I'm trying to increase the volume. We are a little. Just hold on a second. Maximum. Okay, I think we can hear. Okay, Chris, go ahead.
Okay, so I just had a question. The results that you had about the heat waves, did I catch it right that you are comparing between the simulations that have the observed SST and lateral boundary conditions as one set, and then another simulation that has the climatological SST and essentially a form of climatological boundary conditions. So in that case, I guess in that case, it may be difficult to attribute the changes in the heat waves to just the effects of the SST because the lateral boundary conditions were changed as well.
That's right.
Yeah, but you could say the lateral boundary conditions were the effect of SSTs, which are outside the domain, right?
Right, so yeah, that would be the effects of the, I guess, remote SST.
Okay, SSTs that are not in the domain. So you can think of them as together.
Perhaps it's a remote influence.
So I guess is there any anything to suggest that the changes in the heat waves may be from the local versus the remote SST? I know it's hard to separate those two in the simulation since both are changed at the same time.
I need to think about that, how to separate the two effects. What immediately I want to check a little more. So I'm not how I have done. So I want to study how the natural boundaries essentially in that case, in the climatological versus infrared case, how is that atmospheric conditions affecting the inland, but I'm yet to do that.
Okay.
It's a little difficult to separate both of them.
Right. The climatological lateral boundary, is it?
I guess maybe maybe the year 1993 that may give some clues, because if I'm remembering correctly, I think that there's another set of simulations in which just the lateral boundary conditions are changed.
Yeah, for
Right.
the 1993 case. 1993 case.
But I think I think when Tarun gave the talk, people were saying 20 years is barely enough to do extremes. So I think you could look at 1 year, even if it's a few ensemble members, people are not going to buy the extremes argument.
Yeah, that's true.
And for your case, you weren't looking at extremes, looking at mean and so on. So you can get away with it. But for extremes, it's pretty hard to the small sample.
Yeah.
Ling, do you have any questions? Nope. So Rachel, can you hear us? Rachel, can you hear us? Okay, any questions here? Yeah.
Soil moisture? Okay.
I will write something maybe I'm not when the I think I'm so that almost right now. Yes, sometimes the heat waves are
You mean right there?
yeah.
So that's ending actually. It could be. So I think,
No, but in that case, where it's right in the middle. Not every time. Sometimes.
yeah, I think soil moisture, I think in this case would be because of the precipitation, evaporation, ground runoffs. So it could be that, I don't know, maybe just there was a small precipitation happened in the first part. No, means for these peaks, like, if you see that there's a almost instantaneous increase in soil moisture. It could be
So this is soil moisture from the model.
from the model.
It turns rain all the time. Any other question?
Yeah, I think in this case it's kind of visible, like, decrease. Though there were like peaks in between, but the temperature was high.
So the more common thing is it rains, it cools. If it doesn't rain, it doesn't cool. That's the most common. People are looking for the impact of soil moisture on weather. Or it's an impact, but it's not any particular event. It's not that.
Like people have studied like the bigger heat wave events, like 2003 European heat wave events. People have linked to land atmosphere interaction and and droughts as well.
Yeah, droughts obviously because it's very long term, it's clear feedback. Droughts. But these things last
They don't last.
They don't last for long. So the time scale of these things is short compared to time scale of solid life. So these things can happen in between. Okay? So we'll speak next. Yes. You're going to be here? Yeah, you're going to give your trial. So you give your practice. Oh.
Yeah, I wanted to get on the concept.
Oh, okay. Okay, Chris, we are ending it.
Okay, I'll see you guys later.
Yeah.
Bye.
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 Oh,